Let's take a look at 7.1 graphing exponential functions, looking at our parent graph of y equals b to the x, where b is greater than 1, indicating it's a growth. The table of values for the parent graph is going to be -1 and then 1 over b, 0 and then 1, 1 and then b. And just to give you a rough sketch of what it would look like, it would be an upward curve where the tail end gets real close to the x-axis but doesn't cross it. That is called an asymptote. And because it gets close to the x-axis, the equation to that is y equals 0. And let me clean that up a little bit. Y equals 0. Which means my domain is -infinity to +infinity from left to right. My range is starts occurring, my y values start occurring with my graph at 0 to infinity. The equation that we have is y equals 4 to the x, so my parent graph, and that's going to be -1 and then 1/4, 0 and 1, because anything to the 0 power is 1, 1 and 4. So plotting that, y-intercept, 1, 4, there is my exponential growth equation with my asymptote not crossing the y equals 0 equation, my domain, all real numbers, my range from 0 to infinity. Okay, so this one's growing a little higher, faster. Transformations to consider. The first one, if a is negative, that means it's going to be reflected about the x-axis. So all my points from my parent graph will be mirrored downward. If a is positive, I'm sorry, my bad. If a is bigger than 1, it's going to be a stretch. It's going to grow faster. If a is less than 1, it's going to be a compression. And that is an R. If H is negative, just the H, because the formula is always X minus, then I'm going to go ahead and move my X values to the left. If H is positive, that means I'm going to move to the right. Now keep in mind, it's always X minus. So if you end up with X plus, and change it to X minus a negative H. They're equivalent, so that's where I'm getting that H value moving left or right. If K is positive, it moves up. If K is negative, it moves down. And this piece of the K part will help me also move my asymptote and my range. It'll be according to whatever the y value is. So those are the transformations. Let's look at an example that has the transformations with it. So I always graph my parent graph. So -1, 1/2, 0, 1, 1, 2, 1/2, 1, 2. So there is my parent graph, but then I'm going to transform it. I'm going to be looking at this 1 is -1, so that means I'm going to be going to the left, and because this is a -5, I'm going to be going down. So every single point, I'm going to go to the left 1 and down 5. 1, 2, 3, 4, 5. This middle point, go to the left one, and then 1, 2, 3, 4, 5. The third point, I'm going to go to the left one, and then 1, 2, 3, 4, 5. So there is my new graph. Notice my asymptote is at y equals -5. My domain, my range, my 5 looks like an S. Okay, moving on. Let's look at decay. Decay, y equals b to the x, where b is between 0 and 1, so less than 1. Same points, everything's the same as the other one. You'll just notice that it'll look like this, but everything else is the same. So it'll end up being low on the right side. Still the same asymptote and everything. In the example, 2/3 is my base and is less than 1, so we know it's a decay. So my x value is -1, which means it's going to flip this 2/3, my parent graph, to 1 over 2/3. So keep it, change it, flip it. 1 times 3/2 is 3/2. 0, 1, 1, 2/3. So at -1, it's going to be 3/2, which is 1.5. 0, 1, 1, and 2/3, 0.67. So there is my parent graph, but then I'm going to go ahead and transform it. I'm going to go 3 spaces to the right, since it's positive, and I'm going to go up 1. So let's see here. 3 spaces to the right, 1, 2, 3, and up 1. So there's that first point. The middle point, which was my y-intercept, now gets moved 3 spaces, 1, 2, 3, and up 1. And then the third point gets right 3, 1, 2, 3, and up 1. So there is my transformed equation, my domain, -infinity to positive, my range from the k value to infinity, my asymptote is at y equals 1. The whole graph shifted upward 1. I have this formula in growth and decay where the amount, A sub t, amount is what I'm looking for in terms of time. A is my initial amount. 1 plus or minus r, that whole quantity is my factor, which would have been my base in the growth and decay formulas. The r alone indicates a rate, which they give it to you as a percent, but then change it into a decimal. The t, which is my exponents, is in terms of time. It could be a year, 2 days, whatever time may be. The amount that I came up with, or the example I came up with, is not an amount, but as an attendance amount, not just money or population, but it's an attendance amount. So I'm looking at the attendance in terms of the number of games during this season. Well, for some reason, this number came to mind. 23,500 people attended the first game. It declined, and that's why I have a minus in the problem, by 5%. And I put G because I didn't know initially how many games. So there's my equation. I can graph that by making a table of values, putting in decimals. I figured out that there were 15 games involved, and I wanted to know what the attendance would be. Still the same initial amount, still the same decline of, in my rate. So now I have a growth decay factor of 0.95. And in 15 games, what would the decline be? So this would be, once I put in the calculator, what it would be, 10,887 people is what the 15th game would have held if the decline was steady. In the calculator, please remember you do order of operations. You do your exponents first, and then whatever you get, you times it by your amount. So see if that works for you. Please ask tomorrow in class if you have any other questions, and rewind if you need to.